Welcome back, everybody. In this video, we're continuing to work on section 3.6, starting by looking at some examples. So our first example here, we're finding the zeros of a degree 3 polynomial. So kind of the plan would be to take a look and see, okay, is there any way of factoring this polynomial? And if there is, we can factor it and use the factor theorem to find the zeros. But I don't see any common factors, and it doesn't look like it would yield to factoring by grouping either. So there's that. So then the next thing that I would try would be the rational zeros theorem to see, okay, what are any possible rational zeros this thing might have. So that's without being able to factor or anything like that, then the first place I would start would be with the rational zeros theorem. So possible rational zeros will look like fractions, and their numerators will be factors of that constant term, which is 15. So plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15. And then the denominators will be factors of that leading coefficient, which luckily for us is just ones. So it's going to be plus and minus 1, 3, 5, and 15. So I would just try some of these. Start with easy ones like ones. So let me try the 1 and negative 1. We'll go from there. So we're going to do this. You can try this by directly substituting. Again, I'm going to do this by division because if it happens to work, then I will have partially factored our f of x. So this was 1x cubed minus 7x squared, 17x minus 15. Okay, our 1 drops straight down. We're going to multiply and add. 1 times 1 is 1. Negative 7 plus 1 is negative 6. 1 times negative 6 is negative 7, negative 6. 17 minus 6 is going to be 11. And then 1 times 11 is 11. And I can tell negative 15 plus 11 is negative 4, which is not 0. So 1 didn't work. Let's try maybe negative 1. Sorry that there's not really any kind of magic way to make this go faster. Fortunately, synthetic division itself does work pretty fast. So that's pretty good. One thing that's kind of nice is that when you can tell already that it's not going to work, like this one, you can see, okay, well, I'm getting 25. It's going to be not 0 here. You don't even really have to finish it. You just need to go as far as you are able to tell that it's not 0. So that one wasn't 0. So forget that. So let me try 3 next. And then we'll go from there, maybe negative 3, and then we'll go after that. So 3, there's negative 4, negative 12. Now that's looking better. Yeah, that will work. Okay, so we were able to find that one of the zeros is 3, and in so doing, we've also partially factored our f of x. So we know 3 is a 0. Okay, and then if 3 is a 0, then x minus 3 is a factor. So f of x will be x minus 3. That was one factor because 3 is a 0. And then this 1, negative 4, 5 is going to give us the rest of our quotient. That's going to be x squared minus 4x plus 5. Okay, and so now our goal is to get zeros, but taking a look at this thing is now degree 2. So I want to look and see, okay, well, is it going to be possible to factor this thing? And if so, great. And if not, we'll try the quadratic formula or something. You could still try the rational zeros on this remaining part, but at this point, since it's degree 2, it's easier just to try other methods. So trying to factor this thing, we would need to find two numbers that multiply to positive 5 and add up to negative 4. That doesn't sound like it's going to work. So let me try another method. Okay, so I'm going to set that equal to 0, and then we'll just solve that away. So we haven't done completing the squares, and I feel like doing completing the square, so I'm going to do that. So I'm going to push that 5 over to the other side as a negative 5. We're going to complete the square here. So half of negative 4 is negative 2. Negative 2 squared is 4. So we're going to add 4 onto both sides. So then the left side now is a perfect square, so we can factor that as x minus 2 squared. The right side is just negative 1. All right, so now you can see that we have the left side is squared and the right side is -1, so we definitely have complex solutions here. So x minus 2 will be plus or minus the square root of -1, but we know that's I, right? So x minus 2 equals plus or minus I. X is equal to 2 plus or minus I. So in all, our zeros ended up being 3, and then 2 minus I, 2 plus I. So there's our 3 zeros. On this one, I didn't use Descartes' rule of signs, so I could have used it, but I didn't use Descartes' rule of signs to narrow down any of our rational zeros. I probably could have. In fact, let me go ahead and put that on now, just so we can have an extra example of what Descartes' rule of signs tells us. So Descartes' rule of signs, we would want to look for the variations in sign. So taking a look at our original f of x, it goes plus to minus, okay, that's 1. Minus to plus, that's 2. And then minus to plus, plus to minus, that's 3. So there are either 1 or 3 positive zeros. And then the f of -3 would be negative x cubed minus 7x squared minus 17x minus 15. So that has no variations in sign. And so there will be no negative zeros. I guess if I had done this first, then that we could have skipped the part right here where we checked to see if -1 was a zero. Because if I had done Descartes' rule of signs first, I would have known that there's no negative zeros. Okay, so what ended up happening was we had 1 positive zero, no negative, and then 2 complex zeros. Okay, on to our next example. Okay, so in this one, it says factor this polynomial completely and then find all the zeros. So we want the factored form and also what the zeros are. So this one, it says x to the 4th power plus 3x squared minus 4. We want to factor this thing, and there's going to be 4 zeros and 4 linear factors. One thing I'm noticing is that in the structure of this, that there's 3 terms, and the exponent on the highest degree term is twice as much as the exponent on the second term. So for this one, we're going to try another technique of making a substitution. So we're going to do this. Let's pick another letter. Let's let W or U is often used for this. We're going to let U equal x squared. Okay, what's U? By definition, we're just defining it to be x squared. If U is x squared, then x to the 4th power will be U squared. Okay, so if we've made those changes or substitution or those definitions, then we can substitute in place of x to the 4th power a u squared. And then in place of x squared, we'll have a u. So our original polynomial, after we've made those changes, looks like u squared plus 3u minus 4. And that's something that we are able to factor, right? It's just a regular factorable quadratic. So we need to find 2 numbers that multiply to -4 and add up to 3. So think about that for a minute. You should get plus 4 and minus 1, right? So double check if you like, multiply that out, and you'll get the polynomial that we started with. So then we can undo the substitution at this point. Our u is equal to x squared. So this will be x squared plus 4 and x squared minus 1. All right. So we wanted to factor this thing completely. So if we do factor for just real numbers, we'll have x squared plus 4. That doesn't factor using real numbers. And then x squared minus 1 factors as x minus 1x plus 1. Okay, there's the factored form we needed to give. We are able to give all the zeros, though, as well. So the zeros will be -1 and 1. And then also we'll need the zeros of x squared plus 4. So x squared plus 4, we'll set that equal to 0. so that x squared equals -4. So taking square roots, x will be equal to plus or minus the square root of -4, and that is 2i, plus or minus 2i. So we'll have minus 2i plus 2i. So you'll notice here we had 4 zeros, and we had 3 factors if we just leave our coefficients as real numbers. If we wanted to factor it using complex numbers, we could write that as x minus 2i, x plus 2i, x plus 1, x minus 1. Okay, and that would give us our full factorization in terms of linear factors. Okay, one thing that is good to note, and helpful fact, is that if you have a polynomial that has rational number coefficients, like virtually all of ours have been so far, and you know it has an irrational number 0c, then the conjugate of c is also a 0. So suppose that we have f of x, which is x squared minus 5. We're going to find f of square root 5 and f of minus square root 5. So f of square root 5 first. That will be the square root of 5 squared minus 5. The square root of 5 squared is 5. And so we have 5 minus 5, or 0. So the square root of 5 is a 0. So I don't have to do any work. I could just say, okay, well, f of minus square root 5 is going to automatically be a 0 also. Because if I know that the square root of 5 is a 0 of f, then its conjugate has to also be a 0. We saw that happening in our prior example as well. The two complex solutions we had, 2i and minus 2i, those two conjugates, complex conjugates were both solutions. And the same thing happens with irrational zeros. If you have one irrational zero, then the other one, its conjugate will also be a 0. Okay, we'll have another example of that right now. Only this time we're going in the other direction. It says we want to make up a polynomial, and it's supposed to have minimum degree. So we're going to try to make the degree as small as we can. And we want it to have rational number coefficients and zeros of square root 2 and 1. So if it's going to have 1 as a 0, then I know x minus 1 has to be a factor. And if the square root of 2 is going to be a 0, x minus the square root of 2 will be a factor. If we stop right here and I multiply this out, let me go ahead and do it actually real quick. So this would be x squared minus 2 root x minus root x, sorry, minus just a single x, and then plus root 2. If you multiply that out, you can see that we have a, how did I get root 2x? That should have been root 2 x's. We end up with a irrational coefficient, but this said we're trying to make up a polynomial that has rational coefficients. In order to make it so that we end up with rational coefficients, we have to add in that other 0. So we'll have x plus the square root of 2. Minus the square root of 2 is going to be another 0. So this will make it so that we end up with fully rational coefficients, which is what we wanted. Okay, so let's go ahead and multiply that out. So I'll have x minus 1, I'll do that later. The x minus root 2 squared will come next. So we have x minus, and then we have the square root of 2 squared, x squared. That was the difference of squares formula I'd used right here. We have a pair of conjugate binomials, x minus something and x plus something. Multiplying that out together, we get x squared minus that square root of 2 squared. Okay, so now that will give us x minus 1 and x squared minus 2. And then finally multiplying this out, we'll have x cubed. That'll be our first. And then minus x squared minus 2x plus 2. Okay, so there's our polynomial with rational number coefficients and the prescribed zeros. Okay, another theorem comes next. This one is kind of helpful, and we saw an example that related to this on the prior slide. So this is the linear and quadratic factors theorem. And what it says is that if you have a polynomial that has real number coefficients, and virtually everything in this class does, it can be factored into a product of linear factors or irreducible, which is not factorable, quadratic factors that have real coefficients. Okay, so as an example, we're going to try this one. It says x to the fifth minus 16x. We're to first factor p of x into linear and irreducible quadratic factors with real coefficients. So let's do that first. So that's x to the fifth power minus 16x. So what I would do first is factor out that common factor of x. So you're left with x to the fourth power minus 16. That x to the fourth power minus 16 is a difference of squares. So that will be x still. We still have that x. And then we'll have x squared plus 16. No, x squared plus 4. X squared minus 4. Okay, so we factored that x to the fourth minus 16 as a difference of squares. Let me just make that a little neater. Okay, so using real number coefficients, the x squared plus 4 piece doesn't factor any further, but the x squared minus 4 will factor as x plus 2, x minus 2. Okay, so that is our answer to the first part. We factored it into linear factors and irreducible quadratic factors with real coefficients. For part B, we're going to go a little bit further. It says factor p of x into a product of linear factors with complex coefficients. So what that means is if we allow ourselves to use complex numbers, then we're going to be able to completely factor it into a product of linear factors. So I'm taking the answer for part A as my starting point because we've factored it already partially. So the only other piece that's factoring is this x squared plus 4. So that will factor as x plus 2i, x minus 2i. Okay, remember when you're factoring, you can always double check by multiplying. If you're not sure on that, go ahead and multiply out that product of binomials and you'll see that we get what we want. Okay, so that does it. We're able to factor this thing into linear factors using complex number coefficients. So that's the thing, is if you use complex numbers, you're going to be able to factor any real number coefficient polynomial into a product of linear factors. If you just want to use real number coefficients in your factorization, that is, if you don't want an answer in terms of i's, then you can get it down to something that is degrees 1 and 2. Okay, and then that is the linear and irreducible quadratic factors theorem. Okay. All right, so the next part we're going to be working just on working through several examples. So let's try this first part first. The directions, this is from a different textbook, so just so you know. It says finding a polynomial with specified zeros. Find a polynomial with integer coefficients, so we'll get integer coefficients that satisfies the given conditions. And I thought that we would do number 39. And the polynomial is going to be called Q. It's going to have degree 3, zeros of 3, 2i, and minus 2i. So let's try that. Okay, so if we know what the zeros are going to be, then that means that we know right away what the factors are. If a 3 is a 0, then x minus 3 will be a factor. And then it has complex zeros of 2i and minus 2i. Okay, so then let's go ahead and multiply that out. I'm going to deal with the complex part first. So let me just hang on to the x minus 3 piece first. So then here, let me multiply this out. We haven't done it in a little while. X squared, I'm going to use FOIL for this, okay? First will be x squared. We'll have 2ix for the outers, minus 2ix for the inners, and then the lasts will be minus 4i squared. Okay? I just saw that I used square brackets for that. That was an arbitrary choice, okay? It could have been parentheses. Okay, so now here we have x squared. The plus and minus 2ix's add up to 0. And then our minus 4i squared. Our minus 4i squared, our I squared is itself negative 1. So that will give us just plus 4. X squared plus 4. Okay, so now multiplying this out further, we'll have x cubed and then minus 3x squared, 4x's, and minus 12. Okay, so that will do number 39 for us. Okay, that went by pretty quick, so let's do one more that is maybe a little bit more steps to it. So let's go ahead and do, how about 42? Okay, 42 looks good. 42, it says Q has degree 3. Okay, so it's another degree 3 one. And it has zeros of -3 and 1 plus I. So again, if -3 is 0, x plus 3 will be a factor. And then since 1 plus I is a 0, then we'll have x minus 1 plus I as a factor. And so the thing is that for one thing, since this thing has degree 3, it's going to have 3 linear factors and 3 zeros. And we're only told what 2 of them are. So what does that third one have to be? So the thing is, if this thing is going to have real coefficients and it has one complex 0, then the conjugate will have to also be a 0. So the other 0 has to be at 1 minus I. So our other factor will be x minus 1 minus I. Okay, so that's the setup. We'd have to do a little manipulating to get this into kind of a finished product looking thing. So I'm going to multiply out the complex part first. It turns out to be a little bit easier if we rearrange things a little bit. So what's going to happen in this first step is I'm going to distribute the negative that you're seeing here and here. Those two negatives are going to get distributed. So we'll have x minus 1 minus I. Then we'll have x minus 1 plus I. Okay, and then our reason for doing that is so that then I can reassociate these. We'll have x minus 1 in 2 places. And so this thing now is a pair of conjugate binomials. So we can say I know a plus b times a minus b is a squared minus b squared, right? So we're going to use this difference of squares formula to multiply that out. Our x plus 3 still sits there. We will have here our x minus 1 squared. And then we'll have minus I squared. Okay. All right, so then our thickness changed. We'll have x plus 3 still. And then here, x minus 1 squared, you can use perfect square trinomial formula on that. Okay, that takes care of those 3 terms. And then minus I squared itself is equal to -1. So this will give us a plus 1 in the end. Okay, so now we're getting there. X plus 3 is still there. X squared minus 2x plus 2. Okay, so now we need to multiply this all out. You can use a box method or the distributive property, whatever you like. I'm going to use the box method this time. So I'll make a box that has 2 rows and 3 columns. I put the add-ins for the x plus 3 down the left side, and then the add-ins for the second factor across the top. We're going to multiply to fill in the boxes. And then let me make sure that's right. I was talking and writing at the same time. Okay, and so now we can just write down all the terms. So starting at the highest degree term first, that's x cubed. We'll have plus 1x squared, and then minus 4x's, and a 6. Okay, so this time we built up our polynomial and has 1 plus I and 1 minus I and negative 3 as zeros. Okay, let's try one more of those. It says find all the zeros of this polynomial, and I figured we would do number 50 right here. Okay, so our polynomial p of x looks like x cubed plus 7x squared plus 18x plus 18. Okay, so find all the zeros. Okay, real and complex. So on this one, taking a look first, I don't see any common factors to all 4 terms. And this doesn't going to factor by grouping either. I saw both of the last 2 terms had an 18, which gave me some hope, but the first 2 terms did not. So factoring is not going to help. So then the next thing I would do is maybe the rational zeros theorem. So let's start thinking about rational zeros. So they're going to be fractions. The numerators will be factors of 18. And sadly, 18 has a lot of factors. So 1, 2, 3, 6, 9, and 18. Is that all of them? 1 and 18, 9 and 2, 3 and 6. Yeah. Okay, so that's all of them. So counting the negatives, there's a dozen of those. So this time I think it'd be a good idea to see about using Descartes' rule of signs to see if maybe we can just limit some of that. So let's see if Descartes' rule of signs tells us anything. So here, I don't see any variations in sign in the whole polynomial, right? So if there's no variations, that means there's going to be no positive zeros. So that's great news, actually, because instead of having 12 possible rational zeros, now there's only 6. We don't have to consider any of the positive ones anymore. Let's see about p of minus x. So that'll be minus x cubed plus 7x squared minus 18x plus 18. So it goes minus to plus, back to minus, back to plus again. So there's 3 variations. Okay, so we're going to have 1 or 3 negative zeros. Well, we won't get exactly 2 anyhow. So we'll have 1, and then maybe 2 complex, or maybe all 3 will be negative. But we're guaranteed to at least get a negative one. And so what we can do is just start going through those negative numbers we had. So we had negative 1, negative 2, negative 3, negative 6, negative 9, and negative 18. So this is the trial and error, dividing over and over and trying to get lucky part. So I would again start with small numbers like 1 and then go from there. But if you have some insight maybe that tells you that some other number would be good to try, then maybe you want to do that. All right, so I'm trying negative 1. It was 1x cubed, 7x squared, 18x, and 18. Okay, so the 1 goes straight down. Here we have negative 1. There's 6, negative 6. See, this isn't going to work out, right? So we get a remainder of 6 this time. Okay, so it's not 0, so we can forget about that. So negative 1 is off of our list. So we can forget about that. Let's try negative 2 now. So there's negative 2, there's 5, 3, 21. That's getting worse, isn't it, right? And that's negative 42, so no, that's not going to work. Negative 3. Negative 3, 4, negative 12. There's 6. Now that's getting closer. There we go. All right, so we finally got one. Negative 3 is a 0. So we're able to partially factor our f of x. What was it? I was calling it p. So our p of x looks like x plus 3, based on the fact that negative 3 was a 0, and then x squared plus 4x plus 6. Okay. All right, so there is our partially factored directions. It said find all the zeros, so I'm not going to stop there because we haven't found all the zeros yet. So to find the zeros of the last part, we're going to set this x squared plus 4x plus 6 equal to 0. And so we're going to solve that. So you can, it doesn't factor. So instead, we can either use the quadratic formula or completing the square. I want to show you another example of completing the square. So I'm going to take that plus 6 and we'll subtract 6 from both sides. Okay, so now I need the left-hand side to be a perfect square. So we're going to take half of this 4. That's 2. 2 squared is 4. So we're going to add 4 to both sides to keep the equation balanced. So now our left side is guaranteed to be a perfect square. So it'll factor as a perfect square. We'll have x plus 2 squared. That will equal -2. So now taking square roots, x plus 2 will be plus or minus the square root of -2. And then x will equal -2 plus or minus the square root of 2 times I. Okay, so those are our other two zeros. So altogether, our zeros are going to be -3, and then -2 minus root 2i, and -2 plus root 2i. Okay, so that's the end of this example. All right, so that takes us to the end of this video. We'll do one more video in which for this section in which we just do a couple of more examples for this section.